started. I sent this mail this morning already. I'm also putting it up. That's the result of the poll in the class, and that's how we are going to handle extra time. So if you have some additional issues that you want to talk about, either in person or in anonymously by SurveyMonkey, please feel free to do so. Okay. So that's basically what we are going to do. So talking about SurveyMonkey, people do keep putting stuff on SurveyMonkey, and I keep actually getting basically writing. Whenever somebody writes something, SurveyMonkey tells me, then I go look it up. So those are some of the most recent comments. I really have there are 23 responses from the beginning of the semester. I'm just showing you that to tell you that even though there is no easy way of getting back to people who put a comment, because after all, that's the whole point of being anonymous, you can be rest assured that I did read them. Not everything can be followed, but I definitely think about it. Okay, so that's one of the issues there. This is the midterm statistics. The midterm grades have been posted, and we are not returning the actual exams to you yet, because as we agreed, you are all going to be given an option to do like an extra homework version of the same video. Okay, so after that deadline is over, it has to be set up. I think Mario is going to do it as soon as he could. Once he's set up, we will tell you that it's up, and then we will give you a time limit, and then this will be an auto-graded homework. Okay, so you know that you got some answers wrong, but if I also show you which specific answers you got wrong, that sort of kind of defeats the whole purpose. So we decided that we will have that there. Okay, so that's what we are going to do. And those are the actual statistics. There were some changes, some regrading that had to be done, and then there was actual statistics. And then eventually, after the homework thing is done, we will give you okay. Okay. So any questions? Any questions? Yes.
So these are posted on Blackboard?
Yes. Did people see them already? Did anybody see? Yes, some of them did. Okay. It's been posted on Blackboard. Any other questions? Yes.
Jeff Hinton says that the neural nets are passed and that.
Yeah. So Jeff Hinton is known to have. I mean, the joke about Jeff Hinton is that for every month for the last 18 or so years, he will come out of his office yelling, "I found a theory of how brain works." So every month it's a different theory. Clearly, we will talk about the fact that, as I mentioned, there's a very important point to keep in mind that neural networks have the word neural in common with neuroscience. That's about it. Seriously. Okay? And it's very important for you to understand that. And again, one of the things I'm hoping to do is to at least make 120 people who will talk about AI having known something about it. Okay, the world is right now full of millions of people trying to talk about AI without actually understanding what the heck they're talking about. Because that's part of being a sort of in a hyper bubble of interest in AI. Okay, so while I did make the connections to neuroscience that there are, for example, as we'll discuss in a minute again, the Terminets did have some connections, motivations from Hubel and Wissel's original experiments, for example. But in fact, in this slide that I just sort of skipped here at our last class, it's actually a very interesting history. It turns out, for example, that neuroscientists also know that backpropagation is probably not happening in that way. This is like a huge big thing. I mean, Hinton actually has a whole bunch of, if you look up YouTube, Hinton tries to argue that maybe, in fact, backpropagation is possible for brain. But most people don't think that backpropagation of the kind that gradient descent that we're talking about actually happens in the brain. Okay, so which is kind of very interesting because way back, this is the history of neural networks, as is the history of AI, as is the history of science, is full of false starts and some people who actually came up with a great idea not getting the credit in the end because somebody else rediscovers it. Columbus rediscovering America. So in this particular case, what happened is a guy called Fukushima, not the nuclear reactor, but a person. Fukushima actually looked at this background of Hubel and Wiesel experiments and essentially realized, hey, we can actually write a neural network architecture which sort of has this convolutional architecture. Okay, so he did this back in early 80s or before. Okay, the only thing that the reason his didn't work, it turned out that he tried this idea and it didn't work. Now there is this whole question about tried and didn't work. This will keep coming, and then of course he has tried and it worked. That's not the way science is supposed to be. You should know why something works and why it doesn't work. But right now we are in engineering phase. Okay, so essentially Fukushima actually tried convolutional neural networks, and it did work for him. And there actually could be many different reasons why it didn't work. For example, today we will talk about why is it that suddenly neural networks became big in 2012-13 time frame as against before, given the fact that they've been around forever. Okay, we'll talk about that. But one specific reason that people think might have been the reason why he wasn't going anywhere is early 80s when we tried it, he actually did not use backpropagation to train these networks. So he essentially had something very close to a convolutional network architecture. But he chose not to use backpropagation because neuroscience tells us that backpropagation doesn't happen in visual cortex. And he got screwed because it didn't work. And then early 90s, Jan LeCun essentially redid the same thing and he said, to heck with the neuroscience, let's just do the backpropagation anyway and see what happens. And it so happened that by that time, of course, the computational power has become better. There was, for example, MNIST database with a large enough number of handwritten digits. Those are two important things that will wind up being, that we'll talk about again. Plus, of course, essentially he threw in backpropagation. And whatever the reason, it actually worked. And in fact, for a while, postal service, one of the biggest, it was actually that original thing in 90s was called LeNet. And LeNet basically was used by post office to actually read like addresses, especially the zip codes. Okay, handwritten zip codes. Okay, that's about it. Even in 90s, basically when convolutional networks were working, nobody really cared, honestly. So Jan LeCun was in Bell Labs, and then Bell Labs actually exploded, and there's this great Bell Labs diaspora, who went on to different places, and he wound up going to NYU and hung around there and waiting basically. And we'll see how by 2013 a bunch of things came together, and then we could write. So this is actually the problem with science in general. You don't know which idea finally will work. So if you didn't know that neural networks are going to work back in the 80s, thinking right now that neural networks are the only things that will work and nothing else will work in future is stupid. Because suddenly when did you become that particularly perspicacious about future? We are not as a species that great. We just basically. Okay, so in terms of so going back to your original question, yes, this is not actually connected to neuroscience. Neural networks are not really connected to neuroscience. Okay, and so you can come up with all sorts of ways in which maybe you can take better inspiration from neuroscience. One of the strange things is what's his name? What is his name? Lee and Sweden. I think Sebastian Sweden. Sebastian Sweden is actually a neuroscientist. He's hanging around right now in Princeton. He used to be at MIT. And he's very well known for those of you who have done any data science stuff for something called non-negative matrix factorization. He came up with the idea how to do matrix factorization such that the factors are all positive. All the numbers in the matrix are all positive. Okay. Sebastian, he came up with that, but he's actually a neuroscientist. And he gave this talk once, and in fact he goes around saying that the connection is bidirectional. So in some sense right now, they use convolutions or various image recognition things coming from neural networks to actually analyze the brain scans to maybe understand what brain is doing. Okay, so it's a strange situation where basically it's not so much that neural networks are influenced by neuroscience. In fact, neuroscience may be helped by the stuff that happens. Okay, I mean, as far as whether or not Hinton is right, who knows? But he has a good track record. So, okay, any other questions? Okay. So what I'm planning to do basically is run you through these couple of slides that we talked about last time, and then go deeper into some actual implementation issues of convolutions, and then talk about a couple of interesting points. Right now, when people think of neural nets and learning and AI, most of the people who just are reading the newspapers think all of it is just perceptual intelligence. It's just basically working on images and voice. Okay, but intelligence is of course much more than that. And in fact, many of the interesting ideas related to convolutions are actually wedded to the visual data. Neural nets in particular and convolutions in specifically are wedded to the image data. They don't work for any other data. So for example, this very idea that you're doing convolutions with this kernel, it makes only sense because there is locality in images. Not all data has that kind of a locality. In particular, convolutions haven't been all that useful even for something like text data. They're pretty useful for voice data, but not for text data. Because text is actually much higher level. Voice is basically a signal. Okay? So we will try to understand what else is missing. At least we should understand what are the limitations. And then basically, my hope actually is that I can complete the convolutional networks discussion probably towards the middle or later half of this class, and then we shift to logic, which is a completely different topic, and then from propositional logic, we'll start talking about propositional logic, and from there we come to probabilistic propositional logic that gets us to Bayesian networks, that gets us to Bayesian learning, that gets us to understanding what the heck is actually happening in ideas like problem. Okay, so that's basically where we're going to go in the remaining classes. Okay, so we pointed out that the big thing about convolutions is reducing the number of parameters because you're using the same kernel with the same weights, but in different, and you're applying it to different parts of the image. We pointed that out. We said that this comes, the motivation comes from neuroscience. Loosely speaking, I just talked about the fact that in fact, if you really went with the true motivation, you may not have, it may not work because in fact, Fukushima tried it exactly the way without the back propagation, and that didn't work, at least at that time. And then we showed these examples last time about what is actually happening in convolutional nets, where essentially you have an image which is a bunch of intensities, okay? And then first imagine it's just a grayscale image, so it's just a bunch of intensities. And then you have a filter, which is this yellow one, and that filter has, as it's moving, you can see these numbers, 1, 0, 1, etc. Those are the weights, okay? During the use of the convolutional network, this filter is applied to every region of the image. And when I just said every region, there are some details to be worked out. What does it mean? So you start from here, how much do you shift it, for example? That is the idea called stride. And also another issue is, are you only going to shift this on the image that's been given to you, or are you going to do zero padding? That means act as if this image is part of a bigger canvas, okay? Where everything else on this side and this side are zeros, and the real image starts here. And it turns out that zero padding is important in particular, because without the zero padding, as you saw right now, when you convolve in this particular case, you get as a result a smaller data structure, which is not the same size as the image. Okay, in the last class I pointed out that you actually reduce the size yourself using the max pooling, which is basically taking max of the value in each particular 4x4 or k/k kernel. Okay, that does actually deliberately reduce the size of the data structure. But this one doesn't have to if you put 0 pattern, and we will see that in a second. But in this particular case, actually it does. And then of course, the numbers here, this number 4 came because when you put this particular, when you put this particular big 3x3 one on these 3x3 submatrix, and you did that product, you multiplied each corresponding entry of the image matrix with the kernel matrix, added them up. If you add them up, that's what you will get, 4. This is what convolutional nets are doing at, in computing this basically convolutional layer. Okay. After that, what happens is that when this comes, then you might actually submit this to. So convolutional operation is a linear operation. It's just multiplying weights by the image numbers. Neural networks must have some linear operation somewhere. Otherwise, basically, they're not going to be able to get all possible functions. You understood that, right? We talked about this. So what happens is after the convolutional layer, you typically actually have like a max pooling layer and a thresholding layer. And in most convolutional networks these days, they use ReLU as the thresholding layer. You could use sigmoid, you can sigmoid, or you can use tanh, anything which applies to these numbers and basically thresholds them, non-linear. And then that then becomes the input for the next convolutional layer, and then next max pool, and then next ReLU. And then a bunch of these layers will happen, at the end of which, in essence, the image you started from becomes some other smaller data structure. Call it image, but it just doesn't look like an image to our eyes. It has some sort of higher level features encoding. At this point, you take that as the input to a fully connected layer. And the fully connected layer does classification. Okay? So that's how convolutional nets do. And in explaining it this way, you can also realize that actually it was true for this fully connected network too, that if in fact this is the layer, if in fact this is the final layer that is doing the classification of what the digit is, then what are these other layers actually doing? You can imagine that they are converting input through these layers to some other representation. We don't know what that representation is, some other internal representation. It's a different set of features that somehow got extracted, which are then being used to make the classification. So in general, you can think of any multi-layer neural network as doing feature extraction in the first k layers, and in the last few layers it is doing, in the last layer in general, it's doing classification. You can think of that. And that particular view becomes even more obvious, I mean, even more like even more vivid when you do convolutional nets, because in fact conv nets here, in fact, they have the exact same kind of fully connected layers everywhere, except I'm saying these guys are doing features and this guy is only doing classification. But had this been a convolutional network, then all these layers will be conv, max pool, and the threshold, conv, max pool, threshold. Okay, so and those layers themselves are different, they work differently, they're basically taking the total structure into account. And so it becomes clearer for you to see that what they're bringing out are essentially some sort of features in the images. And this is a very useful piece of information because we'll come back to later on an idea called transfer learning, which actually I'm very excited about. It's a very simplistic idea, honestly. But it winds up saying, well, if you have a large big network that you trained on, let's say, to learn cats and dogs, now you need to kind of train some other network to see whether a particular X-ray shows that the person has a particular metastatic cancer or not. That's also an image. In one case, there are cats and dogs images, the other is X-ray images. Now, you could start by saying, let me just basically train the network with a whole bunch of X-rays. Unlike cats and dogs, there are not that many X-ray images. You see what I'm saying? And one of the things that we'll talk about is the fact that neural networks are extremely data intensive. They wind up taking a large amount of data to actually learn a code. Okay, which worked out well when you had data like the cats and dogs, because the internet is full of it. But then when you go to something like radiology, there are not that many examples. So one idea might be, if I learned a huge big network, to train the network on the cats and dogs, let's say that's about 150 layers. In fact, one of the most recent ImageNet winning ideas is this idea called ResNet, which has 150 layers. And you take 145 or so layers, remove the lowest level layers which are actually connected to the output, and say start from there and say, yes, they are getting some kind of features. And the features that you extract from dogs and cats pictures may not be that different from the features you might be extracting from radiology pictures. How do I know? I don't know, I'll just try it out and see. And I'll try it out, I'll use this held out data and say, hey, I'm doing much better than the highly paid radiologists. Which is why, my go-to thing is, mothers, don't let your children to grow up and become radiologists. Because that job is out. Essentially. Okay? Right? Because, machines can basically do it better. Right? Okay? So, but that actually winds up being the transfer learning idea, and that's very connected to the fact of viewing earlier layers as, in essence, computing some kind of features. We don't know what those features are, but the network is doing something. Okay? So, that's basically it. This is the stuff that we taught last class, and I'm just going to go. And then, of course, I also pointed out that, we saw this one too, that in fact, as you do convolution on the images, at least in the beginning stages, what comes out looks like some kind of a blurred version of the image, in essence. So that makes you happy that in fact convolutions are actually capturing some kind of features. But then in a 150 layer network, as you go down and down and down, you don't know what those features are. By the way, actually, so if there's this notion of, I'll come back to these slides in a minute, but let me show you this slide. This one, by the way, is three of the latest and greatest convolutional nets that have done well in ImageNet benchmark. Remember, ImageNet benchmark has its own problems. As I said, it's full of dogs and cats. But that has become the way people actually evaluate the progress in this field. And in fact, back in 2012, this was the top one is called the AlexNet, and it was Alex. As I said, these guys have names harder than mine. So he actually wound up trying neural nets on the computer vision benchmark, which is basically this ImageNet. Okay, and he essentially wound up getting a much bigger improvement in terms of the recognition accuracy, the way they were actually captured. By the way, you have to understand that the way ImageNet actually evaluates is this thing called the top 5 error rate. Okay, so you show a picture. This picture, according to the ImageNet trained network, would be one of 1,000 different classes. You basically ask, what are your top 5 guesses to the network? So whatever are the top 5 guesses that the network has, if the true guess, the true label as given by humans is in any of those top 5, whether it is in the 5th or in the 4th or in the 1st level, you get a point. That's how you calculate the accuracy of the network overall. So that's why it's called top 5 accuracy. It's a very strange thing. In fact, for example, I look at one of you and say, yeah, you must be a person or a dog or a donkey. And I'm right, apparently. And in fact, I could say, you might be a dog or a donkey or a person. I'm not talking about you. But anyway, so the point is, I did put person somewhere in the bottom, so I win in the top 5. So that's how essentially currently we are capturing the evaluation. Okay? Top 5 accuracy. And in fact, it's not necessarily the case. We don't normally think that a picture is like equally likely to be a person or a donkey or a dog. Because we have large amounts of background knowledge. If I'm seeing this picture in the class in front of me, I haven't had many donkeys attending my class for quite a long time. So probably donkey is out actually. Do you see what I'm saying? But the machine doesn't know. It's basically just computing what is the most likely label. Okay, so when they make mistakes, they can actually be crazy mistakes. Okay, keep that in mind. Now, so, AlexNet was essentially 8 layers. We'll talk about what happens to these layers in a minute. This is the ConnectNet. The last layer will be, last few layers will be essentially fully connected layers. But the first few layers will be convolution, max pooling, and thresholding. Typically, they do. Okay, so that was AlexNet and did it quite well. And then I guess by 2014, Google team did something I believe called InceptionNet, which did better. And then as I was keeping track, of course things are changing still. But right now, essentially in 2015, Microsoft had this idea called ResNet, basically residual connection networks. Okay, and that thing has a nice 150 layers. 150 layers. So this is a deepening. The deeper the network, the better it seems to be, basically. Okay. And furthermore, it has a 4.95% top 5 error rate, and humans apparently have 5.1% error. This you can see it as a bug or a feature. Okay. I think the fact that humans have 5.1% error, honestly, I think that means they have a life. They actually can do things other than just differentiating between hundreds and thousands of different kinds of dogs and birds. Okay. However, that as it may be, in fact, we have become superhuman on the ImageNet data. Okay. Right. Now, in this particular case, keep this in mind. So when I was telling you about this transfer learning idea, what I'm saying is, so this is the input side. The image is being shown here, and this is the output side, where the classification is being brought up. Okay, now if you think of that as up and that as down, right, then you have to make sure, you have to realize that the features extracted that are closer to the image are very low level features. Things like edges and blobs. You still have some sense of what is happening. The picture that I showed you, that animation, that was very close to the beginning picture. Right? It was applied to the image directly. So when you just transform the image, you can still see what is happening visually, a little bit. When you come here, you have no clue what it is seeing. You can try to visualize it, but it doesn't tell you much. And we just assume that they must be high-level features. Okay, so that's the terminology. Low level, high up the net, and high level, lower down, close to the classification. The bigger, more important thing is to realize whether layers are closer to the input side or closer to the output side. If they're closer to the input side, they must be lower level features. If they're closer to the output side, they must be higher level features. Okay, now here's the interesting thing. Actually, since we got it here, one of the things that's happening in ResNets, you will see, even though of course this is a kind of almost a cartoonish compaction of the actual network architecture, you do see that it has these skip connections. Right? Normal networks just have first this layer is connected to the next layer, is connected to the next layer, is connected to the next layer, is connected to the next layer. That's feed forward. That's what we agreed upon. What ResNets are doing actually is they are connecting, in addition to connecting this layer to this, they are also making one connection from here to here. That's a skip connection, right? That's sort of like this guy is not only influencing these features through this standard way, but can also influence them this way. Now, anytime I put these connections, of course, the weights for those connections have to be learned by the gradient descent. Okay, and a whole bunch happens there. But I assume that you already understood that gradient descent works on this network. I will spend one more, hopefully some amount of time after this initial discussion, to talk about how in fact gradient descent backpropagation can be done mechanically. Okay, and then some of the magic will be done at that point. But the interesting thing is you are making these skip connections. And it turns out people tried it. Let's see what happens. And they had a kind of an intuition that maybe it will help, and it actually helped. And once it helps, you make a great theory around it. Okay, and the theory basically right now is one of the problems is as you start backpropagating on a really large 150 layer network, the signal, the gradient signal is going to start changing things here. And by the time it reaches there, it becomes weaker and weaker. So the error signal is the gradient signal. And it becomes weaker and weaker. And it takes much longer for the higher level guys to actually train them. So it takes, and we are talking about, millions of iterations versus multi-millions of iterations. And so the idea that they had is because of the skip connections, actually you can make the gradient signal reach to the top much faster while it is also making the lower guys change. So in the original architecture, you get these parts better before you start getting those parts better in terms of the weights. With these skip connections, in some sense it happens together. It was an idea, they tried and it worked. You see what I'm saying? Okay? But you can kind of understand what we wound up doing. By the way, is this still a feed-forward network or is it a recurrent, a bidirectional network? Feed-forward, it's still feed-forward. It's just that not a sync, it's not a linear chain, it has branches. Yes?
So, if gradient descent's going through each layer and then also going through the skip connections, does that mean gradient descent's happening twice for some of the nodes?
There is no such, yeah, yes, in some sense, okay, so that's what actually, hopefully, if I get to the point where I show you how backpropagation occurs automatically, you will realize in essence that for this point, like here, right, the gradient signal can come once through this path and once through this path. And when that happens, you essentially, there are ways in which the gradient signals can be combined. Okay? Again, part of, I want to show you another slide before we go forward. Okay, not this. Oh, this is the stuff that I want to show you about how the backpropagation can be done mechanically, but we'll get to that later. I want to show you something else. Oh, yeah, this one. Keep this in mind. Alfred Whitehead said this, and to some extent, we built this little piece by little piece by little piece. At the level of perceptron, you can completely understand every piece, about how the gradient descent is happening. Okay, when you wind up having this 150 layer network, you have to hope that by that time you understood how to do gradient descent mechanically. Okay,